Hello friends. Friends, today we will discuss the fourth boundary condition for electromagnetics, that is Bn1 equals to Bn2. This is the last boundary condition in the series of boundary conditions. Okay, so let us start with the discussion. Now here we are discussing the boundary condition of B. Now what is B? B is magnetic flux density, okay, having units Webers per meter square. Okay, in the last video lecture I have discussed about the boundary condition of the electric flux density. I will share the link in the description box. Okay, so the statement of this boundary condition is the normal component of magnetic flux density is continuous at the surface of discontinuity. Okay, that is Bn1 equals to Bn2. In the last lecture I have told you about what is the meaning of normal component. Normal means the perpendicular component, perpendicular to a surface. Okay, so this boundary condition can be derived with the help of Maxwell's second equation, that is Gauss law for magnetism, that is integral of B dot ds equals to 0, that I have derived already and will share the link in the description box. Okay, integral of B dot ds equals to 0. Now let us derive this result. Now consider a cylinder, okay, and this is the shape of cylinder, and the gap between these two caps, flat surfaces, is suppose delta x, and suppose this is delta s. Area of this cap is delta s. And if we will draw a boundary here, okay, this is the boundary. Fine. Now if the magnetic flux is entering through this is second cap, this is first cap, this is medium 2, this is medium 1. Okay, below this boundary is medium 2, above this boundary is medium 1. This having characteristics epsilon 1 mu 1, sorry, epsilon 2 mu 2 sigma 2. This having characteristics permittivity 1, permeability 1, sigma conductivity 1. Okay, if the magnetic flux is entering to this surface, and suppose it is Bn2, normally it is entering this surface and normally it is leaving through this surface. Okay, Bn1. Fine. Okay, so the amount of flux entering to this surface is equal to the amount of flux leaving to this surface. This is basically Gauss line magnetism integral form, integral of B dot ds equals to 0. Okay, now we will expand this. Now what should be the direction? Suppose this direction is y direction. Okay, this direction is y direction. Okay, so this is positive y direction, and what should be this? This is negative y direction, this is minus y direction. Okay, now flux is entering to this surface, that is Bn2 is entering. Now what is the direction of this area element? Okay, if we have anything that is cylindrical, and suppose we have a pen, and pen has a cap here. Now if we will try to displace the cap, it will go outward. So direction of the area element is always outward. It's always outward, and in this case this is outward. This is opposite to the direction of the magnetic flux density. Okay, so this is in the direction of minus y direction. So minus y direction means Bn2 direction is j cap, delta s direction is minus j cap, opposite direction, or the angle between these two is 180 degree. Okay, so in other terms we can write down BD as cos of 180 degree. Cos of 180 is -1, so it will become minus B delta ds, minus B and 2 delta ds, or by expanding this plus. Now here the direction of B and 1 is in the positive y direction. Direction of delta S is outward. That is a positive y direction. Okay, so it will be B and 1 I cap, j cap dot delta S j cap equals to 0. So it will become B and 1 delta S minus B and 2 delta S, because the dot product of J with J is, what is this, is 1. Okay, so dot product of J dot J is 1, dot product of I dot I is 1, dot product of K dot K is 1. Okay, you have done in your lower class. So Bn1 delta S minus Bn2 delta S equals to 0, or Bn1 minus Bn2 delta S equals to 0. Okay, so Bn1 minus Bn2 delta S equals to 0. Now if AB is equals to 0, then either A is equals to 0 or B is equals to 0. So in this case, either Bn1 minus Bn2 is equals to 0 or delta S equals to 0. But delta S cannot be 0 because it has some area. So what we will get, Bn1 minus Bn2 is equals to 0. That is Bn1 equals to Bn2. This is our result. That is a normal component of magnetic flux density is continuous. Continuous means that both these components are equal across a boundary, and this is the fourth boundary condition for the electromagnetics. Just remember this diagram, try to make this diagram, remember the direction of the flux and the area element, then you will solve it. Okay, otherwise B dot ds means BDS cos of 180 degree plus BDS, what should be the direction of B and 1 and delta S? It is 0, cos of 0 degree. So it will be minus B and 2 delta S plus B and 1 delta S. Okay, and again you will reach that result. This is equals to 0. Okay, so you can do by this method or you can do by this method. Both the methods are same, and you can derive the result by using any one of the methods. So this is all about fourth boundary condition. If you have any doubt, please share in the comment section. Thank you. Thanks a lot.